Thank you for joining us. And my name is Tom Creasy. I am with Caliper Corporation. Also with me today is Dan Morgan, our product manager. My association with TransModeler has been on the user end. I was a user for really since it was in beta version, the very beginning. Dan has been with TransModeler from almost near the beginning, and he is our product manager. And so Dan will be discussing. If you were with us for the first webinar, we really talked about some of the basics, TransModeler basics, simulating HCS files with TransModeler. We showed our traffic impact analysis tool. We demonstrated traffic signal timing and optimization in TransModeler, and some of the basic things that a user would do using simulation. So our webinar today is on advanced traffic simulation, and it would really be the next steps beyond the basics. So Dan's going to talk about this progression of things like instead of turning movements, using OD matrices and doing dynamic traffic assignment and some applications of that. So with that, I'm going to turn it over to Dan and let him take you through the topics for today.
Thank you. So good afternoon, everyone. Thanks for the introduction, Tom. I'm going to dive right in and, as Tom mentioned, walk us through the sort of standard state-of-the-practice steps one might use with TransModeler to do or conduct analyses that require a little bit more development than, say, a simulation based on turning volumes. So for a simple or simpler analyses where we might just be looking at an intersection or a corridor or other small areas in which routing and route choice are not really of much consequence. Perhaps we're just interested in progression or operations along a series of traffic signals or something of that nature. Now we want to take this to another level and add several more degrees of complexity and throw in some challenges to the mix, if you will. So we're going to start with OD matrix estimation. So if we're modeling an area in which that is too large really to make simulation based on turning movement volumes practical, and I would argue that that happens at much smaller sizes than many of us might think. We really need to be able to estimate origin destination matrices. And if we want to simulate projects, proposed projects that might change the route choices that drivers make because it will impact capacity and travel times and delays, then we need to be able to simulate the origins and destinations of trips and route choices that are sensitive to the delays that the drivers experience. And I say all those things, I may sound like common sense, but I say those things to contrast it with the case of simulation based on turning volumes, where the paths that drivers or vehicles take are really just synthesized from the volumes and don't necessarily follow any rhyme or reason or logic. So in order to set the table for an origin destination matrix estimation, we need a couple of inputs as a starting point. And we're using a study area north and west of Las Vegas here to demonstrate these concepts. And the study area that we're looking at in the map was first identified in a travel demand model, which is one way we might begin to estimate the origin destination pattern of trips through our study area. So for a moment, I'm going to step away from the TransModeler window and show you how this might be set up in a planning model. For instance, in a transportation planning platform like Transcad. This is a sub area we've identified through what we call selection sets on the highway layer from the regional travel demand model for Clark County, Nevada. So if I zoom out of it, we'll see this is the entire region of Clark County. The green dots we see in the map represent the centroids of about 1,650 traffic analysis zones throughout the region. And the darker green lines and blue dashed lines are lines we've selected to be the focus of our microsimulation analysis. So one of the ways we can estimate the OD pattern for the study area is on what we call a subarea analysis in Transcad. In other planning platforms, it may be called subarea extraction, or there may be other terms to refer to it. TransModeler does not require that you perform the subarea analysis in Transcad. It will be convenient if the region in which you're doing the study happens to be a Transcad user. The data formats are the same, so many things will transfer over seamlessly. But I just wanted to make that point in case you happen to be doing simulation in a place where a competitor planning software is used. That wouldn't be a roadblock to using TransModeler to do the microsimulation. So we have in the map on the left a selection set of the subarea, and on the right we have a matrix of the OD origin destination volumes for different classes of trip predicted by the travel demand model. So as I mentioned before, it's about a 1,650 square matrix. And the subarea analysis that we'll perform, I won't run it here, but I'll just go through a couple of the motions to show you how a matrix like this might be produced. The subarea analysis will do a traffic assignment on the entire network and add some additional bookkeeping to keep track of where traffic enters and leaves the subarea. So if we were to run a subarea analysis, in this case, we do a multimodal, multi-class subarea analysis so that we can retain information about the OD patterns of the different classes of trip. In this particular case, we're talking about drive alone, shared ride or HOV2 trips, and shared ride or HOV3 trips, and a single truck class in this particular model, although other models may have light, medium, and heavy truck classes. So we'd add the classes that we want to assign to a list, and maybe set up other settings such as passenger car equivalents or link exclusions to get to prevent single occupant vehicle trips from using HOV links and things of that sort. All of the basic traffic assignment parameters are also identified, such as free flow times, capacities, alpha and beta, etc. And so most of these inputs are just your standard static traffic assignment inputs. The key difference here in the subarea analysis is that we'll take those selected links and create a subarea from them. So beginning with the regional model with 1,600 plus rows and columns in our matrix, what the subarea analysis will produce for us in this case is a 66 square matrix where the rows and columns are made up of 44 external stations around the boundary of the subarea and 22 centroids inside the subarea. So if I were to run this subarea analysis right here, we would produce a matrix as an output. And that matrix would look like this one. So this matrix now is 66 by 66 and contains 3 matrices in it, one for our drive alone trips, shared ride 2, shared ride 3, and trucks. Other ways to create a seed matrix for our OD matrix estimation might be to, if the study area is manageable enough, make a license plate survey or Bluetooth survey, or potentially going to Streetlight or some other vendor that can give you an estimate of the OD pattern. However you arrive at that seed matrix, that's going to be the starting point for the OD matrix estimation, which is then going to make adjustments to the matrix in an effort to better fit traffic counts that you've collected for the subarea. So that's going to be the second main input that's required for running the ODME. So I've opened the matrix here from the song side, my simulation map, where we've already used high resolution aerial imagery to define the geometry. We've imported centroids and centroid connectors from the planning model, and we've entered signal timing information at all of our intersections as well. So basically, the supply model is set up and ready for simulation, but we need to estimate the traffic demand. So in order to do that, we'll need to set up the traffic counts that we'll use to make adjustments to this seed or input matrix to the ODME. And this model has already been populated with that data. And just to show you where that came from, we'll look at a table of the segments in the network where we have traffic counts. This is a table with a record for every road segment in the network. And for a subset of road segments, we have traffic counts, and we've imported data from the traffic count data, including the metadata describing the location of the counts, and 15-minute counts in each interval of the day. However, when we run a static traffic assignment, we're going to be estimating, when we run an OD matrix estimation, we're going to be performing a static traffic assignment, which means we're going to be loading a peak hour or a peak period matrix and trying to estimate a sum count across that peak period or peak hour. So while the 15-minute counts we're looking at here are going to be instrumental in a subsequent step, I just wanted to point out the origin of the traffic counts prior to running the ODME. So those 15-minute counts have been summarized as attributes of the links. So I'll open a table of the links in this database. And just to recap from the previous webinar, in TransModeler, roadway links can be divided into segments anywhere you have a lane drop or a lane add or a change in lane width, anything that changes the cross section of the road, but where you don't have the intersection of a third link or side street, for example. So in this table, we have a record for every link in the model, and we've got the summary counts for AM and PM peak periods. In this particular case, we're going to look at an OD matrix estimation for a 2-hour morning peak period. So we'll be looking at the AM counts, and we can select the link features in the map that have traffic counts on them and take a quick scan of that in the map. So I'll select the records by condition. And I've got a saved query that I've entered earlier. So we're going to select all of the links where the count in one direction on the link is not null or has a valid count, or the count in the opposite direction is not null. And we'll name this selection set counts. So now this table is showing us the subset of 23 links in the model that have traffic counts on them. So I'll close that table and we'll take a quick look at the network to see how sparse these counts are. The better the distribution of the counts and the greater the number of counts, the better success you'll have with OD matrix estimation, where success should be measured by the ability to match the OD pattern in the field. If you've only got 1 or 2 or 3 or a very sparse set of counts in your network, your ODME will produce a very good fit with those counts, but that won't necessarily make it a successful ODME exercise, because the ODME can skew your OD pattern to match the counts in whatever way it sees fit. So using ODME will require some experience and some comfort with the various controls and parameters you have to to steer, if you will, the ODME towards a more reasonable solution, which is to say one that doesn't skew the seed OD pattern or the trip length distribution that's characteristic of the input seed matrix. So this is a fairly typical case. The number of counts we have here covers most origin destination pairs, and that's going to be another key sort of prerequisite. If you have any origins and destinations in your model that don't have counts anywhere in between them, there will be no basis for the ODME to adjust the trips in those cells. So having enough counts to cover all of your origin and destination pairs is sort of a bare minimum, and the OD matrix estimation, when we run it, will give warnings if that's found not to be the case. So we have these 23 green links that have traffic counts on them, and we have a seed matrix that's our starting point for an estimate of the OD pattern. So what we'll do next in TransModeler is identify what are the fields in our link table that contain the counts. So to do that, we'll visit the project settings. There's a network tab where we can choose the link variables that we want to be available to us in the OD procedure. So I'll filter this list for the counts, and I'll add the AM count to the list of selected fields. And this is particularly for an AM scenario. If we had a PM scenario in this project, we'd do the same to add the summary PM counts to its link variable list. So we can see this project is already set up to simulate a peak period from 7 to 9 a.m. And what we've just done is identified the count fields that contain the peak period counts between the same start and end time. So having done that, we'll be able to take the next step, which is to launch the OD matrix estimation, which we can do from the demand menu, OD matrices, OD matrix estimation. Here we'll identify, again, just as we saw with the sub-area analysis dialog box in Transcad, we'll see a lot of the same inputs. So what drives the OD matrix estimation in TransModeler, and in fact in most, if not all, commercial OD matrix estimation tools on the market, is a static traffic assignment. And I'll come around back to this point in a bit. But that's why we see a lot of the same static traffic assignment variables specified in this dialog box. We've got our free flow times and capacities and alphas and betas. Except here in TransModeler, those values will be derived from road classes. So major arterials and collectors and ramps and freeways, et cetera, will have lane capacities, free flow speeds, and alpha and beta parameters that will feed these inputs. So what we want to tell TransModeler here is, what is our seed matrix? We want to, because this is a static traffic assignment, but it's also a single class traffic assignment. So let me back up for a second. If you want to run a multi-class OD matrix estimate, do that in the travel demand platform that you're working with. But what we'll do is run a single class OD matrix estimation to match the counts. In this case, and in many cases in practice, we may not have classified counts on which to base a multi-class OD matrix estimation anyhow. So the steps that I'm going to follow would pertain to that use case where you've got counts, but you don't know from those counts what portion of them are trucks or autos, etc. So what we need to do before we can fire up this OD matrix estimation is sum up the multiple classes into one summary matrix. And with the matrix as the current window, we can do that in one quick step by clicking a quick sum button on the main toolbar. And what that does is sums up the matrices from our 4 different classes here into one grand total matrix, which it calls quick sum. So with that out of the way, let me return to demand OD matrices, OD matrix estimation, where we're going to choose that grand total matrix as our lead, the AM count field that we identified in the project settings. We want to tell TransModeler what the length of the analysis period is, and the rest are those static traffic assignment variables that I mentioned briefly. If we want to help the OD matrix estimation by providing additional information like turning movement counts, we can click the options button to do so. And we'll also have the opportunity there to identify weights for different sets of counts. For example, if this is a 2018 model we're estimating, but some of our counts were taken in 2015, we might give a lower weight to the 2015 counts and a higher weight to the 2018 counts. Or if some counts were taken using technologies that are more error prone, we might give those a lower weight. So just in the way we provided the link count fields, we could also provide a weight field if we chose to do so. We can also provide an additional matrix that would constrain or bound the extent to which we allow the seed matrix to be changed. And that will allow us to apply cell by cell constraints. So for instance, if we don't want the ODME to overestimate short trips in order to improve the fit with the count, but we want it to maintain the input trip length distribution, we might supply lower constraints for shorter trips and higher constraints for longer trips and so on. And there are tools for doing that in TransModeler as well. So those are just some of the options we might exercise when running the ODME. So what the ODME is going to do is perform a static traffic assignment to convergence, which in this case will be up to 500 iterations or of 10 to the minus 4. And once it's performed that assignment, it'll compare the assigned flows on all the links where there are counts to the counts and determine whether the cells should be scaled upward or downward to better fit the counts on the shortest paths between the corresponding origins and destinations. So we can ask TransModeler to perform this adjustment iteratively up to a maximum number of iterations. So let's say we wanted to do up to 20 OD matrix estimation iterations. What it's going to do is perform up to 20 traffic assignments and make adjustments to the OD matrix in between each assignment. And the reason that process has to be iterative is once you've made one adjustment, the basis of the counts between a particular origin and destination pair, those adjustments will affect the goodness of fit between other origin destination pairs that also send trips through the same links. So you might impact more than one cell in the matrix with each adjustment. So the iteration sort of converges on a solution that best fits the traffic counts after having adjusted all cells in the matrix. So we'll click OK, and TransModeler will ask for the output folder and file names for the outputs of the OD matrix estimation. So we'll save the outputs in a subfolder that we'll call ODME. We'll create a new folder for that. And we'll append AM to each of the output file names so that we can distinguish the ODME results for our AM scenario from those of our PM scenario. Then we'll click OK, and TransModeler will perform the OD matrix estimation. And for models of this scale, they have to run pretty quickly. Each static traffic assignment will converge relatively quickly. And in 20 OD matrix sessions, we will have arrived at our estimated matrix. What Transmodeler will do next is estimated matrix into a matrix window. It'll also open some additional output files, such as a log of the assignment statistics from the last assignment from the ODME. We'll close that. It'll also open a table of the assignment from the last iteration of the ODME. So what this table will contain are the link volumes that were assigned joined to our link table so that we can compare them with our link counts. So if I scroll to the right, we'll find that two tables are joined together here. Let me show just the link records that have counts. These are our AM counts, and these are the assigned flows. So just in eyeballing the volumes, they look like they're a pretty good fit with the counts. But we can do a few steps better than that. If we go to the Tools Statistics menu, we can create a scatter plot that maps the assigned volumes against the counts. So here on the x-axis will be our AM peak period counts, and on the y-axis will be our assigned flows resulting from the OD matrix estimation. So we'll title this chart ODME AM scatter and label our axes and we'll ask it, in addition to showing a regression line, calculate a relative root mean square error for us. We'll click OK and we'll get a chart that shows a pretty great fit between the assigned flows and the counts. So that's well and good, a step in the right direction. For reasons I'll get into, this isn't the end of the story, but just for the time being, we can appreciate the quality of fit that the ODME predicts. We've got a slope of 1 on our regression line and R squared very close to 1, and a relative root mean square error of under 3%. So all fantastic statistics. But we're about to see that the microsimulation is going to produce a very different result. For all sorts of reasons, maybe everyone in the audience is well aware of, static traffic assignments aren't the best models of operations. They don't account for signals well. They don't account for queuing and spillback at all. And for a host of other reasons, they're good tools for big picture analyses and planning, but they're going to give us the wrong answer if our concern is operations. And in the simulation, drivers are going to make route choices based on the delays they experience, and those delays will be the outcomes of signal delay and time experienced in queue and things of that nature. So the route choices are going to shift away from the predicted shortest paths that the ODME used to arrive at this good fit. But we'll talk about ways we can overcome that difference. But there will be sort of a gap between the static assignment and the microsimulation. And the dynamic traffic assignment is going to help us to a degree overcome that discrepancy. So we'll close this chart and close down the results of that assignment. And we'll close the subarea matrix, which was the seed for our ODME. Now, before we want to simulate this estimated matrix, we want to do a couple of things to add information. Right now, because the ODME was single class, we need to separate the estimated trips back into auto and truck trips. And additionally, we want to use the 15-minute count data that we have to estimate the temporal profile of the demand, because we know that over a 2-hour peak period, the demand isn't going to be constant or flat. So I made a mistake. I actually want to have that sub-area matrix still open because we're going to rely on the travel demand model and the sub-area analysis to tell us what share of trips in each cell ought to be auto or truck trips, at least according to the regional model. So in our estimated OD matrix, where we have just a single estimated matrix that began from the quick sum of the sub-area seed matrix, so it inherits the same name as the seed matrix we started with, so it's called quick sum. We're going to add auto and truck matrices to this OD matrix. So from the matrix menu, I'll choose contents and I'll add an auto matrix. Because we don't have any HOV lanes in this sub area, I'm not going to go to the length of distinguishing single occupant from high occupant vehicle trips, but you can do it in the same way that we're about to see for autos and trucks. So we'll just have an auto matrix and a truck matrix. Actually, because not all trucks are the same, let's at least make an effort to distinguish single unit trucks from tractor trailer trucks. So we'll add 3 matrices. Right now, these matrices are empty, but we're going to use a formula to multiply the estimated matrix by a factor we'll derive from the seed matrix. Basically, the share of the seed matrix that is auto will be applied to the estimated matrix. So we'll choose matrix fill, and I've already got a formula that takes the estimated matrix from the ODME and multiplies it by a sum of the drive alone, shared ride 2, and shared ride 3 matrices, and divides that by the seed matrix's total. So what this part of the equation is the fraction of the total demand in the seed matrix that were auto trips. And we're going to multiply that fraction by the ODME estimated total demand. So that gives us about 41,570 trips of the total estimated 42,492 trips. And just out of curiosity, let's look at the sub-area matrix and see what it predicted as the total demand in this sub-area. So the OD matrix estimation brought the total demand from 63,000 trips down to just under 43,000. So if the OD matrix and these counts are correct, it would appear that the travel demand model overpredicts or overestimates the demand for this sub-area. But we'll leave that to a full-scale calibration and validation to draw that conclusion. So in the single unit truck matrix, we'll similarly apply a formula. And that formula, all we have from the seed matrix is an estimate of the total number of trucks, but we don't know how many are single unit or tractor trailer. So I'm going to make the basic simple assumption that 75% of our trucks are single unit, and then the remaining trips will be tractor trailer trucks, or 25% of the trucks. Okay, so that gives us about 687 single unit trucks. I'm looking at the lower right corner of the matrix to get the sum of all trips in the matrix. When a matrix is the current window, you can choose to show in the marginals the sum minimum, maximum, or other statistic. So lastly, for tractor trailers, we're going to fill this matrix with another formula, which will simply be the ODME total trips estimated minus the auto trips minus the single unit trips, which we've just calculated, leaving the remainder to be 229 tractor trailer trips in our study area. So now we're back to a multi-class matrix that will define the classes of the trips we're simulating. And the next step we want to take is use traffic count data to spread the trips over time. At this point, we can close our subarea OD matrix. We won't be needing it anymore. And we're going to use the segment traffic counts that I briefly showed you earlier, which give us 15-minute counts from the field to estimate what the spread of trips is over our 2-hour peak period. So in order to do that, I've got a selection set, which I've created in a similar way that I showed you earlier for the link counts. And I'm showing the segment records that have the 15-minute count data stored in them. And I'm going to click Compute Statistics on the main toolbar. All that does is takes the current data table and summarizes minimum, maximum, sum, and other metrics for all the numeric fields in the table. And the reason that I'm doing that is I'm going to use the sum of all counts in each 15-minute interval divided by the sum of all counts across all intervals as an approximation of how much traffic will enter our subarea or depart from origins in our subarea in each 15-minute interval. So basically, we're assuming departure times for trips in our model track the 15-minute distribution of the counts. So these columns here are the 15-minute counts for the 7 o'clock, 7:15, 7:30, 7:45 on through 9 a.m. This is the sum of the count in each of those intervals. And the count field is just the number of records that have observations. So I'm going to just hit Control-C on the keyboard and switch quickly to a spreadsheet where I've set up a few straightforward calculations. Because counts go in both directions on a link, on a two-way street, we've got counts for directions spread across two fields. So we sum those two up for each time interval. So this cell is basically just the sum of the trips in each direction in each 15-minute interval. And this last column divides that value by the sum of all the counts so that we can estimate the share of the total number of trips that departs in this 15-minute interval. So all of these values will sum to 100%. And I've taken another step and defined these cells as a named range in the spreadsheet, which I've called curve. And in Transmodeler, now we can open that spreadsheet which I've named curvedata.xlsx. And when we open a spreadsheet in Transmodeler, we can choose to import it or just to open it natively. And we can open a worksheet or a named range. So I'm choosing the named range curve, and I'm choosing not to import it. And that opens those cells into a data table. And now I can import these data points into a curve in our trip matrix settings. So let me show you what I mean by that. So we have our OD matrix here, but we haven't told Transmodeler anything about this matrix, what time period it applies to, which matrices are the autos or the trucks. We've named them, but we haven't told Transmodeler what those names mean. And we do that through the trip matrix settings. From the demand menu, we can go to Demand, OD Matrices, Trip Matrix Settings, and indicate that we want to spread the trips over time according to a curve, which will add a curve tab to our trip matrix settings. And we can click Import to import this distribution into our curve. So we'll choose that curve table that we've opened, use all records from the table, and the time period will be identified by a time field, and the weight or fraction of the demand departing in each time interval will come from this percent column. We'll click OK, and the curve will be imported. The curve can be drawn or manipulated by hand if you want to just enter an approximate curve. But if you've got the count data to support it, then it makes sense to take the steps to try to derive it from that empirical data. Okay, so 14.07 here is the 14% of trips departing between 7:30 and 7:45 a.m. Back on the Contents tab in the Trip Matrix settings is where we'll tell TransModeler which matrices we want it to create trips from and what kind of trips we want to create from those matrices. So we don't want to create trips from that grand total matrix that the ODME produced, because we would be double counting it if we're also generating it from the auto and truck matrices. So recalling from just a few minutes ago, these three matrices sum up to this total. So we won't specify a vehicle class mix for our auto trips. It will take a mix. It will use a mix defined in our vehicle fleet parameters. And for our truck matrices, we'll override those vehicle fleet parameters and produce a specific class of trip or vehicle from these matrices. And had we taken just a couple of extra steps to differentiate between single occupant and high occupant vehicles, then we could identify that for each matrix as well. So I'll click OK. And close down some of these windows that I don't need anymore. Back in the map, I'm going to temporarily turn off the green coloring of these links that have counts so that they don't distract us. And I'm going to visit the project settings and add this matrix we've just estimated and we've just applied a temporal curve to. I'm going to add it as our input trip table. So on the Input tab in the project settings, I'll click Add, and I'll browse for this matrix. And I'll click OK. So now our model has the geometry, signal timings, and an estimate of the demand. So we have the bare minimum for starting a simulation. So I'll open the simulation toolbar, start up a simulation, and we'll see what it looks like. However, note that right now, since we haven't supplied any travel time information or delay information, all of the trips are making their route choices assuming free flow travel times. And we're going to see that this will cause problems. If I minimize the map and schedule a pause time for 8 o'clock, we can let the simulation run to the middle of the analysis period and have a look at the queuing around the network. So, and while that's happening, I'll describe the next step we're going to take. So we don't want to make the assumption that the shortest path is the best path for all trips. Once the vehicles start to travel in the network and experience delays, they will learn where queues form and how severe they are, and they'll be able to make wiser route choices. So we can think of dynamic traffic assignment is sort of a learning algorithm. We'll run a full simulation and report the average segment travel times and turning delays over short time intervals. That might be 5, 10, or 15-minute intervals. And then we'll use that information to update the route choices before we run another simulation. And we'll do so in a way that converges on something like a dynamic user equilibrium, where drivers will no longer be able to change their routes and improve their travel times. So here we are at 8 a.m. in the middle of the simulation, and we can see pretty long queues forming in certain parts of the network, including southbound here on Decatur Boulevard. If we head east on Cheyenne, fairly lengthy queues will form eastbound there, and southbound on Martin Luther King Boulevard, similarly, queues form. And a lot of that has to do with turning movements whose capacities are overwhelmed. And if you want to study the OD pattern and the route choices that drivers are making, there's a critical link toolbox that will allow us to do that. With that, we can click on a link of interest where we see heavy queues, and we can see all of the origin-destination pairs that are sending trips through that link. And they'll all look like sensible paths, which might give us the impression that no DTA really is necessary. If we were traveling between these same OD pairs, we would probably take these paths. But part of the DTA problem is determining where and how trips might spread to different loading points in a traffic analysis zone. You can see most of these centroids connect to more than one street in the road network. And without any additional inputs to spread the trips among those loading points, they're going to make a route choice that minimizes their travel time as well. But given all these delays and queue links that we see, we'll find that just running a DTA will allow them to learn where the best points to enter the network are. And for now, we'll go on the assumption that these zones represent areas that have a local street network that's not in our model, and they can access any of these points. It is certainly possible that based on the land uses, some of these zones are limited in terms of their intra-zonal connectivity and may not allow for trips to enter at any point they choose. That kind of detail can also be added. Okay, so we have a loading based on the assumption of free flow travel times. I'm going to stop the simulation now, and we're going to run a dynamic traffic assignment so we can estimate those congested travel times that we want to use to inform the route choices in the model. That's really what dynamic traffic assignment is about in the microsimulation context. There are a lot of ideas out in the research and in the practice about what DTA is good for and what its applications are. In the context of a microsimulation study, we want to leverage it to determine the most reasonable route choices of drivers. So to that end, it's a model development step. It's not the end goal. It's not an end in and of itself. Whereas in, say, the planning context, if you were building a dynamic traffic assignment model for your region, you might run the DTA rather than a static traffic assignment and be done. That tells you what the loading is in the network, where you have bottlenecks, where your volumes exceed capacity, things of that sort. But in microsimulation context, we want drivers to make route choices based on an understanding of the congestion pattern so that we can simulate different alternatives. Those alternatives might involve ITS strategies, signal timing improvements, roadway diets, taking away a lane and dedicating it for buses, any number of things that might change the capacity, might bring about a change in route choices. And so the DTA is a tool for helping us determine what those changes might be. So at this point, we can close our estimated matrix, which we've made a few changes to. But I want to just mention briefly that we aren't necessarily finished with the OD adjustment process. We might learn things through the DTA that might take us back to ODME. We might decide we want to apply different constraints or use different weights, or we might just want to make and rerun the ODME, or we might just want to make some minor adjustments to the OD matrix ourselves using tools like the critical link tools that I showed you before. So in order to run a dynamic traffic assignment, I'm going to do one thing here real quick in the project that's going to be a time-saving adjustment. So I'll visit the project settings again. And the project settings, those of you who have used TransModeler before will know that some of the tabs in the project settings are hidden from you so as not to overwhelm you and intimidate. If you're working in a relatively straightforward project and you're not simulating bus or rail operations, you may have no need to enter the transit inputs. Or if you're simulating a corridor in which there are no route choices, you don't need to provide routing inputs, and so on and so forth. Similarly, there's a parameters tab that's hidden by default if you're not going to change any of the model parameters or change any local parameters. So I'm going to show that tab, and what I'm going to do here is change the microscopic model step size to 1/2 second. And what that does is basically going to somewhat degrade the accuracy and fidelity of the microsimulation, which is typically and traditionally run at 1/10 of a second time steps. But in the name of running the dynamic traffic assignment loading way faster, up to 5 times faster per simulation than if it were 1/10 of a second. So I'm going to change that step size to 0.5 and click OK. That'll help us to get through maybe at least a couple of iterations here during the webinar, but I won't let it run for the full length, but we'll run it long enough to get a sense of how long the DTA will take to run for a model of this scale. Recall that this model is going to simulate about 43,000 trips over a 2-hour period, and it will be more the volume of demand you're simulating than the area size that will determine running times. Okay, so earlier we had run a quick one-off simulation and paused at 8 o'clock to see what the queuing patterns look like. What we're going to do now is change the mode of the simulation from that one-off simulation mode to a dynamic traffic assignment. And these modes are ordered in a particular way to follow the flow of a project. In the early going, you might run single simulations just to visually audit the simulation, make sure it's running reasonably well. You may run dynamic traffic assignment to estimate the congested travel times that will become inputs to your model. And when everything is ready, all your inputs are prepared, you'll probably run batch simulations because this microsimulation is a Monte Carlo simulation. Random numbers and probabilistic behavioral models will mean that different simulations will produce different results. So let's go back to dynamic traffic assignment. We'll tell the assignment to run up to but no more than 50 iterations or until it converges on a gap of 0.5%. And TransModeler, like many other DTAs out there, will use as a stopping criterion the percent change in the congested times between iterations. On the principle that once the travel times cease to change, route choices will cease to change, so it won't matter how many more iterations you run, because the route choices will not change. So we'll leave that default target gap at 0.5%. You probably will not need to run more than 50 iterations in any model, and you might even get away with fewer in simpler or smaller models. But 50 is a sort of rule of thumb that we've grown comfortable with over a large body of DTA work. Another thing that we'll do here while we're setting up these DTA parameters is tell Transmodeler where we want to save the outputs of the DTA. So we'll set up a folder to store our congested travel time information. We'll name it DTA. And it's already set up to have AM appended to each of the file names. And I'll click OK. So every time I run the DTA in this scenario, after setting up these output files, it will overwrite these output files, which eventually we will use as inputs to our simulation. So anytime we make adjustments to the model, maybe we go back and change the demand or rerun the ODME, we can start from those previous congested times from a prior DTA. And each DTA will update those inputs, so it effectively turns our project into a self-feeding feedback loop. The outputs of the DTA are already set up as inputs to our simulation. So we'll say OK, OK again, and I'm going to save the project at this point since I've made a variety of changes. I've added an OD matrix. I've changed the microscopic simulation step size to 0.5 seconds, and I've configured the DTA to produce results in a certain folder. Now we're ready to run the dynamic traffic assignment. So I'll do that by clicking the Start button on the toolbar, and Transmodeler will produce the trips and any warnings that might have come across during the initialization. And it's going to run up to 50 simulations back to back, each time updating the travel times that are input to the route choices of the next simulation. And we can also see while it's running that setting a 0.5 second step size makes the simulation very, very fast. So it's running more than 100 times faster than real time, which means in this sort of medium-sized study area, we'll get through a 2-hour simulation in a matter of minutes, if that. Another thing I'll point out while it's running is that Transmodeler is multi-threaded, which means it's going to use all of the processors on your computer and split up the work so that it can run the simulation faster. So it's basically parallelizing the simulation, assigning simulation tasks for different parts of the network to different processors on your computer. So this particular desktop that I'm using now has 20 computing threads on it. I believe that's 10 physical processors with hyperthreading. And you can see it pretty well maxes out the utilization of all these CPUs. And that's partly how it's able to accomplish these running times. While the DTA is running, we'll see that the run times per iteration are just shy of a minute. So again, that's 1 minute to simulate 40,000 trips over 2 hours. The 0.5 second is a big part of that, but we're still simulating the same level of detail, at least in terms of the driver behavior. It's still acceleration and car following, lane changing. The operation of the traffic signals is always going to be 1/10 of a second time resolution, because you may have amber times and vehicle extensions and other parameters that have 1/10 of a second resolution. So while the DTA is running, TransModeler minimizes the map, because another way to speed up the simulation is to take the graphics out of the equation. So by removing the animation, the simulation is able to run much faster. See, right now, as the queuing sort of abates from one iteration to the next, assuming it abates, and this isn't a really congested model, the simulations will also run faster, because it's the number of vehicles in the network at any given time that determines how fast the simulation can run. So the more traffic you've got tied up in queues, or potentially even queuing outside the network, the slower the model will run. So now we're down to about a half a minute per iteration. We can, if we want to observe the DTA, however, while it's running, we can open up the map. We just want to be sure to minimize it when we're done, so that it can regain that speed advantage. But you can see maybe you can't see, I'm pointing at the status bar at the bottom when I talk about this time factor of being 100 times faster than real time. So TransModeler is telling you how many clock ticks in the model are taking place for every real-time clock tick. So with the animation showing, it's slowed down to about 10 times faster than real time. But we can see that the queuing has already dramatically changed. And that could potentially be because, the centroids that were previously loading traffic onto Decatur may now be sending trips to J Avenue or to Valley Drive, or they may just be choosing different routes. The critical link tools can still be used to click on a particular link and see where trips are coming from and going to that are using that link. And as you click on each of these cells, it'll show you the shortest path between these origins and destinations. And in this early going in the DTA, you will absolutely see unusual route choices such as this one. And as the DTA converges, you should see those bad paths go away. But being able to use the critical link tools and other tools to query the paths that drivers are using, we can make sure through visual audit that the route choices that drivers are using make sense. So another way to do that is to use the View Vehicle Path tool on the main toolbar and click on a vehicle in the map to see its origin and its destination and the path it's taking. Another tool that's useful for studying and scrutinizing the route choices are the path tools. And the path tools allow us to click an origin in the model and drag the mouse to a destination. And we can double click to see what's the shortest path between that origin and destination. So they've headed down Rancho Drive and taken a left on Lake Mead Boulevard. But an alternative path might have been to take Cary Avenue or Vegas Drive. And to see why trips might not have taken one or the other, we can add a waypoint in the middle of the route by dragging the path to another street. So that shortest path estimated a travel time of about 17 minutes. We can see that on the path tools. And when I force the path down Cary Avenue, we see the travel time go up to almost 22 minutes. So if we want to now force them to take Vegas Drive across, we see the travel time is about 19 minutes. So as the DTA progresses, all the used paths between all origin and destination pairs ought to become pretty similar in travel time. However, because it's a dynamic traffic assignment and the route choices are dynamic, different route choices might be made at different times during the simulation. Recalling the curve in the matrix, things get a little more congested towards about 7:30 or so. So drivers might be a little more industrious in their route choices during those intervals, whereas later, as things taper off, they might sort of gravitate back towards the free flow shortest path. Okay, so I'll close the path tools, and we treat a certain number of iterations at the start of the DTA as seeding iterations. So during those iterations, it doesn't really make sense to calculate a convergence gap because it won't converge to anything like dynamic user equilibrium that quickly. So this is sort of these are the fact-finding or explorative iterations before we really start testing convergence. So 10 iterations is the default. It's also possible to ramp up the demand from some fraction of the demand over these seeding iterations so that you don't try to load a very heavily congested model with all of the demand in those early free flow iterations. So the seeding allows you to sort of build up the demand. Once you reach the last seeding iteration, 100% of the volume will be loaded. So at this point, so once we had reached those 10 iterations, we'll start to see a convergence gap in the dynamic traffic assignment dialog box here. But at this point, I want to stop the DTA and answer no, that we don't want to take the results from that last iteration, because I've already run a DTA previously, so I'm just going to copy it over where we've told the outputs to be saved. And now we're going to go to the project settings, assume now we've run the DTA to completion. These are the steps we'll take to pull the congested times into our project as inputs. So here we'll choose to show the routing tab. And on the routing tab, we'll choose the historical travel time table, which is one of the outputs of the DTA. This table has a record for every segment and columns for every 15-minute interval, giving the average travel times on those segments. And it goes hand in hand with a turning delay table, which has a record for every turning movement and a column storing the average turning delay at every intersection, also averaged over 15-minute intervals. So we'll say OK. And now our model is set up with the outputs of the DTA, the results of the OD matrix estimation. So the next step would be to rerun the simulation and see how well the simulated loading holds up relative to the ODME loading, which we saw gave us a very good fit with the traffic counts. Now we want to know if, now that drivers are taking route choices that are sensitive to signal delays and queues and things of that nature, are they still using routes that ultimately produce a good fit with the data? So in order to come up with the simulated volumes, we'll go back to those simulation options and choose to run a simulation producing aggregate volumes and speeds. And we can choose to aggregate those volumes in multiple time intervals. Note that you'll also get average speed from this, so that if you have speed data from NRIX or another source, you could also use it to compare bottlenecks and severity of congestion and things of that sort. So we'll say OK. We'll run a simulation. This time, the simulation is going to produce those aggregate segment volumes and turning movement volumes. We'll say OK. At the end of the simulation, it will open those output tables. We'll minimize the map again so that it can run as fast as it can. And then when the tables are open, we can join them to our link table so that we can see the simulated volumes and the counts side by side and produce a scatter plot comparing the simulated volumes with the traffic counts. Okay, so we're about 8:45. The simulation is almost completed. These are our output aggregate volumes. So these are the volumes that actually completed or traversed every segment or completed every turning movement. So these are served volumes, not demand. So they are the most appropriate output to compare with the count data. So the segment volumes and speeds, we want to join to our link counts. And if we choose the join tables button on the main toolbar, we can choose to join link and segment fields together. So TransModeler already knows how to do that. Links and segments are directly related. So we will choose to have the segment. Actually, we'll first join the segments to, let me back up a step. We want to join any table to a map layer first to get the segment volumes joined to the segment table. And then we'll join the links to that table by joining link and segment fields. So segments will be on the left side of the join, links on the right. And we'll look at those segments, just those segments that have counts on them. And we'll go back to the Tools Statistics menu to produce a scatter plot comparing the simulated volumes to the counts. So again, the counts are our AM peak period counts. This time our volumes, model volumes, are simulated. We'll call this the simulation, AM scatter. Still the x-axis are the counts, y-axis are the model volumes. We'll ask TransModeler to calculate relative RMSE, or root mean square error, along with the regression. And we'll see a little bit different spread, still a good slope, relative root mean square error that's probably satisfy many calibration criteria, although some would probably like to see some of these lower data points fall better in line with the counts. So some adjustment may be needed back at the ODME step, or the critical link tools can be used to make targeted adjustments to the OD matrix. So we've run the ODME, we've run the dynamic traffic assignment, and we've fed the simulation project with all the outputs of those steps as inputs to the model. And now we have a model of a particular scenario that we can use, provided we're satisfied with that fit. We now have a model we can run to produce output measures. And if we're going to simulate or prepare other alternatives or projects, we might follow a similar process. So the demand would remain fixed. You'd only run ODME once, but you may have different scenarios in which you need to run the DTA again to capture the changes in route choices that result. And to highlight some of the things that you can do in TransModeler, and that the ODME and DTA and TransModeler allow you to do, I'm going to choose a different project that highlights a variety of applications. So there are tools in TransModeler for modeling ITS operations. So more than just traffic signals, you can simulate ramp meters, dynamic message signs, work zones and incidents, and things of that sort. So to highlight this, we're now looking at a project in Phoenix, Arizona. This is I-17, which they refer to as their spine corridor, runs north-south. South and east of here is downtown Phoenix. And I've placed in the model on the northbound lanes a work zone that closes the left two lanes. And you can see they're sort of staggered. The brick overlaying the left two lanes indicates a closure, and the lanes in the right are reduced to 30 miles an hour. And that will hold for the duration of the morning peak period, which we want to simulate. So we have a work zone toolbar, which we've added this work zone and defined its parameters. And there's also a toolbar for defining those different traffic management strategies. It might be ramp metering strategy, it might be a dynamic message sign strategy, it might be peak period shoulder running. All of these strategies can be modeled out of the box using the tools on this toolbar. We've set up two scenarios here, one that has the work zone but with no strategy. So no information is provided to the travelers about the lane closure, so they discover it as they travel I-17 northbound and react to it at that time. And then we'll show another scenario in which we've added a variable message sign or dynamic message sign upstream that warns drivers that the two lanes downstream are closed. And that gives them time to make lane changing maneuvers to get to the lanes to the right and make better use of the capacity. So you don't have everyone changing lanes at the last second, yielding or leading to a bottleneck that could otherwise be avoided at the start of the lane closure. So this is producing many more trips than we had in the small example we were just looking at. This is a pretty lengthy piece of I-17 and some surrounding networks. So we're simulating about 600,000 trips over a 4-hour AM period in this case. So these toolbars are calculating all the route choices. Given that this is a work zone that might be in place for a period of days, running another DTA might be warranted if you think people might change their routes while the work zone is in place. If you're modeling something like an incident that's spontaneous, then a DTA would not be appropriate because you'd be, again, the DTA is a learning process, and a spontaneous incident, a driver has no foreknowledge of. So the work zone has turned red to indicate that it's active. Those left two lanes are closed, and the vehicles will now when they come within the visibility of the work zone, they'll begin to make their lane changes to move to the right. If we minimize the map again, it will run faster. Eventually, we'll see congestion forming upstream of the work zone, which we can see here. Eventually, this will spill back into downtown Phoenix and onto I-10, which runs east-west through downtown Phoenix. I'll hide the imagery so that we can refresh the map a little quicker. So this is the study area. The incident is here, and the queuing will spill back eventually quite a distance. So if we instead leverage ITS, like this dynamic message sign, to inform drivers that of the changes, then they'll be able to make decisions, and we'll be able to estimate what the impacts or benefits of such a strategy are. The ramp meters, unfortunately, we won't see come online until I think 6:30 a.m. They run during the peak period, but you can just make out that gray circle as an inactive ramp meter. And it's only 5 a.m. right now in the simulation. So let's stop this simulation and look at the operations with the dynamic message sign in place, just to highlight where this whole process eventually leads. ODME and DTA ultimately produces a model in which you can compare alternatives that could be roadway improvements, capital investments, or it could be dynamic or active traffic management strategies. So now I'll switch to the scenario that has a plan in place for the dynamic message sign, we'll start the simulation up and we'll see a different congestion pattern upstream of the incident. It won't save the network from reduced speeds, but it will spare it of the severe bottleneck just upstream of the work zone. And while that's running, since there's only about 8 minutes left in the time we have, I'm going to leave it at that and open the floor to questions that I think, Tom, you're going to quarterback.
Dan.
Yep, go ahead.
Yeah. Yep, I've got some right here. Thank you for those that are asking. Going back to the matrix estimation process, a good question. Is there a reason you summed up the counts in the link layer? Could you have done it in the segment layer as well? And this will give you a good opportunity to differentiate between the segment layer and the link layer.
Yeah. Good point. So let me go to another map just to highlight this real quick. So we actually carved the sub area we were working with earlier out of a regional microsimulation model of Clark County that we developed for the Regional Transportation Commission there. So this is what that model looks like running. Here we're simulating 1.7 million trips over a PM peak. But I'll use this to highlight real quick the difference between links and segments. So here, actually this may be a little more complicated than is necessary. Let's go to a place where it's a little more straightforward. So here we've got a link running southbound. This entire red span between these two signalized intersections is a link. However, we have a left turn bay and we have a change in lane striping. So it's actually divided into 3 segments to capture the change in lane striping and the change in number of lanes. So if I switch to the segment layer, I can see 3 individual segments. And you can store the traffic counts in either the segment or the link layer. It really is entirely up to you. The simulation database can be extended to warehouse your data in whatever way you see fit. However, in Transmodeler 6, we made a change from all the prior versions that requires the counts to be in the link layer as input to the ODME. But if you have the counts in the segment table, it's trivial to transfer them to the link layer for the ODME. And we did that because we saw huge performance gains when we moved towards a more link-based network for routing than a segment-based one, which we had in prior versions of Transmodeler. So for the sake of running the model much, much faster than you could in Transmodeler 5 and older versions, you've got to have the counts in the link layer is the trade-off there. But if you need help transferring data from a segment to a link table, Transmodeler tech support can provide you some quick steps to do that.
Okay, thank you. The next one is a 2-for-1. Is the static path assignment all or nothing? And also in DTA, can there be multiple paths for the same time period?
So I'm not exactly sure whether the thrust of the question is referring to the static traffic assignment in the ODME context. So let me start there. In the static ODME, it's a static assignment, so there is there's only one. Well, there can be multiple paths, but the loading is based on volume delay curves, so it's not sensitive to delays or queues or things of that sort. In the simulation, so it's not an all or nothing. It's running the assignment each iteration of the ODME to a user equilibrium. Once we move to simulation with that estimate of the demand, there is the first iteration of a DTA, assuming free flow time, will effectively be something close resembling an all or nothing. So everyone will choose the shortest path based on free flow travel times. And in 9 cases out of 10, they'll all be the same path. There's still a stochastic nature to the route choice, so travel times are randomly perturbed, so you could get trips using multiple paths even when free flow times are assumed. But once you get through multiple iterations of the DTA, it's no longer an all or nothing. Every trip is making their own route choice based on their perception of the travel times. And I use the word perception because, again, we're randomly perturbing the travel times for every trip to capture different driver preferences and experiences. Drivers are heterogeneous. 2 people departing at the same time between the same origin and destination may still not take the same path. So Transmodeler sort of subscribes to that notion of things. And so every trip is going to compute their own route choice. We don't build up a set of paths for each interval either. Rather, every trip makes their own independent route choice. And that route choice is sensitive to the time they depart. And so it's a dynamic shortest path, so the travel times they expect to encounter on trips downstream on their path will come from the interval in which they expect to arrive at those links. And when they expect to arrive at those links will depend on the accumulation of travel times and delays they anticipated up to that point. So even though the travel times and delays are averaged in 15-minute bins, we linearly interpolate between them. So every driver will expect a travel time that varies continuously between intervals based on when they arrive at a link. So long story short, no 2 trips will ever calculate exactly the same route choice. They might end up with the same path, but it'll be through a different summation of the congested travel times and delays.
Okay. We've got a couple more questions, and one thing I'd like to do, Dan, is be able to provide the kind of contact information and show where where we on our website where we place the first webinar, and then for those that have to jump off for some other commitment, they can do that. And then we can, for those that want to stick around, maybe answer the last 2 questions. Is that suitable?
That makes sense. Yeah. And if anyone has follow-on questions, you can use the contact information that Tom will show.
Okay.
But yeah, I'm happy to stick around a few minutes longer or for as long as there are questions.
Okay. Okay. So on your screen here, you can see our contact information if you have questions for either one of us. And if you want to take a look at the first webinar, we've broken it up into, I think, 5 videos. We're recording this one, and so a couple other questions for Dan. Is there a reason DTA output-informed assignment can't be used as input to the ODME process rather than relying on volume delay function parameters, volume delay flow? That is, circle back after the initial ODME and DTA to then rerun ODME again using the DTA-derived routing as an input to the ODME assignment?
Well, I'm not a static traffic assignment expert. I think there are static assignment procedures that can be sort of warm loaded from travel times of a previous assignment or travel times from a dynamic traffic assignment, as you're suggesting. But the internal mechanism of the ODME is every iteration to run a complete user equilibrium assignment. So it's got to use the volume delay curves to do that. It is feasible and I think more practical. So that's sort of trying to force a static assignment to somehow use the congested times of a dynamic assignment. I think it's probably a more practical way forward is just to develop a dynamic OD matrix estimation procedure. I say just, that it's not as simple as that. There are good reasons why there are no commercial solutions available for dynamic ODME. It's an extremely difficult problem, many more degrees of freedom even than the static ODME problem has to begin with. We do have one that's simulation based that we use in-house at Caliper for project work, but it's not something that we would yet feel. It's a research project, basically, not something we yet feel comfortable putting in the hands of end users. But perhaps down the road, dynamic ODME solutions will become available. It is unfortunate. This is where the state of the practice is. The simulation tools are much better than our demand estimation tools, but this also highlights the need for better data to observe OD. ODME is the main tool we use to estimate OD patterns, but it doesn't have to be the only tool or weapon we have. If we could measure it better,
Okay,
we'd
thanks.
be way better off.
And one final question: is it possible to see the multiple path assignments between the same OD pairs?
It is. So I had shown the way you can click an origin and a destination with the path tools in TransModeler and view the shortest path between an origin and destination. You just click one more button on the path tools and it will show you all of the used paths between that origin and destination. So yes, you absolutely can. And for each one, you can see what the travel times are, assuming different departure times or different user characteristics, say if you're a single occupant vehicle or multiple occupant. So yes, you can do many more things with the path tools than I showed you in the short time we had today.
Okay. Well, I'd like to thank everyone for their questions, for their interest today. We will be having future webinars on TransModeler features. Don't have any schedule laid out for that just yet, so I advise you to just monitor our website at caliper.com in the TransModeler section, or send an email to myself or to Dan Morgan, or also just follow us on LinkedIn, and probably not maybe shorter webinars on single topics. There are a number of additional things that we would like to be able to highlight, the features and capabilities within TransModeler. So again, sorry that we went a little bit long, and I want to thank you all for your participation today.
Yeah, thanks everyone. Thanks, Tom.